you can't really talk about type 1 error without talking about type 2 error. And type 1 error we call the alpha error, the probability of rejecting a null hypothesis when it's actually true. If you test a research question and there's nothing going on, there is a 5% chance or an alpha percent chance that you're going to say, hey, something's going on. And this, you run a little bit of a risk of kind of looking like a jerk and saying something's going on when nothing is going on. Now, I'm not going to give anyone a hard time for making a type 1 error, because I understand that's the rule of the game. It's worth it to cross that field to get to that campsite. If you get struck by lightning, hey, you died doing what you love most. Now, the flip side of the alpha error is the beta error. And the beta error is when there is a false null hypothesis, when something actually is going on, but you fail to detect it. And I always run this joke with the students. I said, if you make an alpha error, the average person is going to think you're a jerk. You went on Oprah and you said something was going on, and then later on it finds out nothing was going on. What the heck was that person talking about? And you and I will be like, oh, they just made a type 1 error. That's no big deal. Now, so what do you look like when you make a beta error? When there's a difference out there and you fail to detect it? Well, you don't look like anything. You failed to detect anything. No one's going to publish anything if you failed to detect it. So you look like nothing. The beta error, it can be thought of in terms of the flip side of it, which is power. And power is the ability for you to detect a difference that is out there. Framing again, what is going on in terms of the truth? The null is either true or the null is either false. We are doing what's called the classical or the frequentist type of statistics, where the null is true or the null is false. And you go out and collect some data and you say, okay, I'm going to reject that null, or I'm going to fail to reject it. And that might be wrong, or it might be right. Let's think about this idea here. When the null is false, when something is going on, but you fail to detect it. You didn't detect it. A type 2 error, the beta error. And like we said, power is just the opposite of beta. It's the probability of rejecting a false null hypothesis. It goes a little bit like this. Let's say you suspect that you have a drug that works. You want to test it. And you come to me and you say, hey, Tibor, give me some money. I want to test and see if this drug works. And I say, well, how much money do you need? And you say, well, I want enough money that'll be worth it, that I'll be able to find statistical significance. And you might rationalize, if I don't have a big sample size, I know I'm not going to have enough precision in order to detect a difference if it's out there. So how much money you need is going to be driven by sort of what sample size you need, right? And so we often go into a study saying, how many subjects do I need? What is my N? And in order for you to figure out what is your N, because again, the amount of money you need is driven by how many subjects you need to get and what you need to do to them, and fixed and variable costs and all that sort of stuff. You need to figure out what your N is. And how do you know what your N is? Well, it's driven by a formula that goes into your alpha level has to be considered. If you have a really strict alpha level, you're obviously going to need a bigger sample size than if you have a really relaxed alpha level. So we plug N in. If you're trying to detect a difference that is really, really big, you don't need a very large N because the difference is really big. If I turned around right now, wait, that's a bad example. Let's say I had two people behind me, and one of them had very short hair and one of them had very long hair. which one do you think is male and which one do you think is female? Well, they tend to, on the average, the difference hair, you can tell. You might be wrong, but you can tell. You don't need that many people to say, am I looking at a bunch of men or a bunch of women? Some people are weird, right? You probably need more than one. But how big of a difference there is, it's easier to detect it. You wouldn't need as big a sample size. And part of this also gets into the underlying variability in the populations. If you went somewhere where a bunch of guys had weird long hair and a bunch of women had nice, cool, short hair, there's more variability in that population. You would need a bigger N. But if you got in a time machine and you went back to 1955, where every man on the planet and had every man in the United States, at least, they had the exact same haircut. So wouldn't need as big of a sample to see if men and women have different length hair. So all of these things go into an equation. And that equation will then say, hey, this is the N that you need. But there's another part that's important. You have to think about what power do you want? As a researcher, you might come to me. I mean, you know your chance of making a type 1 error. It's alpha percent. But you want to think about, I do not want to make a type 2 error. I don't want to miss something if something is out there. So when I say, how much money do you need? You say, all the monies. Give me all the money you have so that I can get as much precision as possible. But I have a problem. If I give you all the monies, I have no more monies for anybody else. I would like to give you enough money that you can do your thing and you might find something, but I also have money that I can have somebody else do their thing. Look, I'm not talking about me. I might be talking about the American Cancer Society. I might be talking about the NIH. I might be talking about a drug company who's trying to investigate a bunch of new stuff. You don't want to put all your eggs in one basket. So we have to sort of decide together of how much power do I want to give you? I can give you all my monies to get as much power as possible. I can give you a tiny little bit, but then you'll have a little bit of power. I want to invest enough in you that you might find something, but I don't want to invest everything in you. And so we kind of agree like, all right, this is the power that you're going to have. And again, this isn't written in stone, but you'll often see people calculate their studies so that they have 80% power. And that's saying that if there is a difference out there, there's an 80% chance I will find it. I might miss it. Now, if you don't want to miss it, then you can up your power. But as you up your power, you need a bigger N. And if you need a bigger N, you need more this. And remember that everything that we do, it's not only about N, it's about the square root of N. So you have to really ramp up that N to get more power. So before a study, you often see all these things get plugged in, and the NIH will say to you, okay, what sample size do you need in order to have 80% power? Now, some of this stuff in here, if you think about it, it's weird. How could you say before you do a study what magnitude difference you're going to see? How could you say before you do a study what variability in response you're going to see? And so now we get a little bit of, you have to come to me and say, give me the money. And I have to read your application and say, okay, that seems reasonable. That smells about right. Here's some money. This should give you about 80% power. Now, the flip side of this is after a study is done, you can leave out a different unknown. You can do algebra. Algebra means the unknown or the missing piece. Once you do a study, you already know your N. Right? Yeah, that's from your study. You can already know the magnitude of the difference, what it actually was, instead of that guess you did ahead of time to see what it might be. You already know the variability of the population. You obviously know your alpha because you said it. And from those things, you can actually calculate, if you have a P greater than 0.05, you can actually calculate post hoc, hey, what was my power there? And this is interesting. If somebody makes a type 2 error, actually, let me say it like that. That was wrong. If somebody has a non-significant result, you might want to look closely and see What was your power? Because the non-significant result might just come from the fact that they weren't using a strong enough flashlight to find what was lost or to find what's there. And this can be especially important when you see people go around saying that this thing is safe. This drug doesn't have side effects. Oh, there's no difference because of that environmental exposure. Whenever someone's trying to sell you a story where they're trying to tell you that the null hypothesis is true, this thing is safe. Be very skeptical, because you know that you can never prove that something is safe. All you can do is say, we have no evidence that it's harmful. And this is a subtle point, but you have to be careful about it. Now, if you want to go and use these tools and make a ton of money and sell out your soul, go for it. Knock yourself out. And one thing that you might want to do is run a bunch of studies that are underpowered. And if you run an underpowered study, you'll never find anything significant. And to the average person, not significant means it's safe, right? But you're smarter, and you would never do that. So power, we calculate when we design the study, and it goes into what sample size do I need? And we talked about this. 80% power is roughly what you want. One thing that's really interesting to me is the variability in the groups dictates a lot about how big of a sample size you need to see a difference. The magnitude of the difference is important, but the variability within the groups is also important. And you can kind of get a little bit of a sense that the difference between the groups, the details on here aren't important, but the difference between the groups make it easier to hone in. As your sample size goes up, you get easier to hone in, and you can better see what the truth is. And also the variability is important. I was watching the World Cup with my son when he was 6 years old, and it was a game. World Cup is a football. It's a game. You kick a ball around. It was a game between Japan and the Ivory Coast. And there was a zoom in, a close shot of a guy doing a throw in from the side. And my son said to me, Dada, what team is he on? And I was like, dude, look, what do you think? Like, you can't tell what team this guy is on? Why? It's because the variability of appearance of all of these guys and the variable appearance of all of these guys, even to a 6-year-old kid, they don't overlap. They don't overlap. Now compare that. What does the French national soccer team look like? Or what does the United States national soccer team look like? Harder to tell. Does this guy play for France or for the US? Does this guy play for Japan or for Ivory Coast? It's a little easier to tell. So when we think about type 2 error, we think about it in terms of power. And we can either calculate before a study starts with the unknown of what N should I get, or if we found a non-significant result post hoc, we can calculate what power did I have. Maybe that could explain why I failed to detect a difference.